Hello and welcome. My name is Vretos Vasilios and today I'm going to introduce you to the new HST3000 multifunctional copper tester. It's the JDSU #1 test equipment for qualifying, verifying and testing copper. Let's now begin our basic copper testing presentation. Together, we are going to introduce ourselves with the methods of procedures as well as different functions of the unit that will make our life easier in regards to copper testing. Let's now begin. HST3000 is ergonomically designed and it can handle many SIM modules that they are coming with a unit. So we have 4 different modules. We have 2 for copper and 1 for optical, as well as 1 for ADSL test and measurements. The modules are easily fitted on the back on the unit and they are securely tied, and as you can see we have the correct insertion shown in the following pictures. If the tab is not inserted in the right place, then the unit will not be able to perform the measurement. Our main priority prior to employing a service on a new and/or existing line is to ensure that the line meets the basic specifications criteria in regards to voltage, resistance, capacitance and current measurements. That takes us to the first most important menu of functionality within the HST3000, the DVOM. This menu is composed of different sort of tests in the following hierarchical order: the ports dialer, the AC volts, the DC volts, the resistance snapshot, the resistance continuous, distance to short, current and voltage snapshot measurements. In the following slides we are going to go through each of the following functions on this menu and how they are used in conjunction or standalone for performing different sort of measurements. AC volts test. Why do we measure AC volts on a line? We measure AC volts to detect the presence of any hazardous voltage, to measure the induced AC voltage current from power lines and other AC interfering sources that may come from power lines, or maybe a high spontaneous AC voltage imposed from another pair, and just simply measure the ringer voltage level to make sure that the line is operating in according to specifications. What do we need to expect when we are measuring the AC voltage? What we are expecting out to measure on a line? The results between the tip and the ring, which is the main and the outer conductor within the pair, should be 0 volts, ideally. Now the tip to ground and ring to ground should be equal and opposite to each other. Anything else about getting these values should indicate clearly that there is an AC signal interference or an unbalanced line. So when we are doing this measurement, we have to have values near to the ideal ones. If we don't get the ideal values, then it's fairly and simply logical that we need to check for other faults on the line. So in the AC volts application, we have different implications. If you get an AC voltage reading from tip to earth of 5 volts and a reading from ring to earth of 15 volts, then either the tip is open or the P leg is longer. This will also introduce noise on the loop. Ring B voltage level can be checked by having the central office ring back on the line. The result should be either 85 volts if we account for older switches, or 105 volts accounting for newer switches. Now we are going to move on to the DC volts test. Why do we need to measure DC voltage? That's another parameter coming into play when we are characterizing a line. You measure DC volts in order to detect and measure at the central office exchange the battery. Or we are making this measurement to see if there is a crossed battery condition on our line. In order to measure DC volts, we have to remove the line battery and measure the tip and ring to ground. That ideally should be less than 3 volts. Anything else will indicate gross battery conditions that we're inhibiting a fault. Now we are going to jump into a video that we are going to show a hands-on on how to measure AC volts using the HST3000. Now we are going to perform an AC voltage test. What I'm going to do is, first of all, I'm going to try to generate a voltage of 20 volts at 0.9 kilohertz, for example. And I'm going to connect the tip, the ring, and the ground just for the sake of demonstrating the range of voltages that the instrument can do. If we go to the first menu, we are choosing the digital volt ohm meter menu and we are pressing OK. Then the unit should be able to, by pressing left and right, you can read the values from A to B, which is the tip to ring, ring to ground, and tip to ground, which is actually 0 volts because there isn't any potential difference in between them. For example, with the battery removed, you get a measurement on tip to ground of 15 volts. This indicates there may be an open in the insulation drawing current from another pair. Let's see the application. To check for span battery voltage, measure tip to ring across several pairs. On good lines, tip to ring will be 48 to 50 volts. Tip to ground should be less than 5 volts, and the ring to ground should be the opposite polarity of the tip to ring, that is minus 48 to minus 52 volts. Now, I would like to demonstrate to you the DC voltage as well test. What I'm going to do is I'm going to generate a steady voltage of 20 volts that I'm going to output, and I'm going to make our unit to test it. So if we go back to the initial menu, that is the digital volt ohm meter, we are going to use display again and we are going to select DC volts. Again, by using left and arrow keys, we can see the respective voltages. So simple as that. Let's move on to the short circuit measurement. Short circuit indicates that leg A and leg B are in contact with each other. To measure this fault, we first of all need to take the line out of service, i.e. to drop the battery at the exchange, so that we can see at the end of the line where the fault is. Or actually, the fault will indicate the end of the line, even though we know the real length of the line. We can run a voltage snapshot. There we should get values that they are less than 3 volts AC to DC between A and B, A to F and B to F. Here we can see some screenshots on the voltage snapshot. is usually caused by a penetration of water inside our legs. That means that at that point where the cut is, the water penetration brings the two cables together, so one is touching the other. In order to specify the short circuit, we need to check the resistance by using the selecting resistance snapshot, as we can see the following pictures. Ideally, A to B should be greater than 10 megaohms. That means as higher its value we are, the better it is. If we find the resistance to be less than 3.5 megaohms, then we consider this situation to be a short circuit. Moreover, sometimes we are experiencing that A and B may also be short-circuited to earth. Then the resistance measurement will look like this. That is, if we see the next picture, the A to B should be 0.046 kilo ohms. B to ground should be 0.061 and tip to ground should be 0.06 kilo ohms. This implies that the previous situation is happening 3 times, as everything is shorted towards the earth. Both leg A and B are short-circuited to earth. Expected values are less than 3.5 megaohms, as we previously said. So here is the example. Let's see at the checkpoints. So the checkpoints is going first to the customer premises and using a PET function to find the short circuit distance to the point of the short circuit. The exchange towards the customer premises. We are using the PET function to find the short circuit from that side. And lastly, we can do a leakage test to blow up these water humidity ingress points that they are causing this short circuit effect. Otherwise, we can run a distance to short measurement to locate the fault. As you can see the following picture, if I press display and distance to short, this should give me the distance where the cable is shorted. Here you have to remember 3 parameters. Left and right arrows are used to change the gauge of the cable. Up and down is to stabilize the temperature to the outer environment. Now jump to a demonstration. Let us now jump to a demonstration on how to perform a short circuit measurement. Now move on to an open circuit measurement. Now we are going to perform a resistance snapshot test. Let's suppose that we are on the customer line, checking the customer's line, and we are on the pit looking towards the customer. We have the simulation fault box. We are going to consider this good line as being the customer's one, and from this point we are going to consider that it's our pit. So it's the pit that we are connecting the actual leads of the unit, and this is the endpoints on the customer premises. For the purpose of demonstrating a short circuit line, I have short circuited the points at the customer premise. So what I'll do is I'm going to connect my leads to the line like that, make sure that they are not touching together, and I'm going to use a good earth point. If you hit the default menu, then you have to press display and select a resistance snapshot. The tip to ring, that is A to B, should be short circuited. As we can see, the value is 0.035 kilo ohms. That indicates that there is a short circuit on the line. So the red to green, red to earth and black to earth is above 99 megaohms. Keep in mind that these values between the red, green, black to green, and all values actually, if the line is good and open, should be 999 megaohms or above 35 megaohms. So at this example we can see that the line is already short-circuited, and we mostly check it for this parameter. Sometimes customers complain that there is no service, either phone or DSL, while both the AC voltage and DC voltage and resistance tests show good results. So here is the following situation. This would definitely mean an open circuit. So somewhere along the way, something happened to the line and we are experiencing an open. There are two ways of measuring an open circuit. In this slide we are going to see the first one. That is the capacitance meter. We can use the second menu inside the HST to do a capacitance meter's measurement. That is to measure the length of the pair up to the point where it's open. When we hit that measurement, then we are getting the results of A to B to be 265 meters. That can be either an open within the length of line that we are measuring, or it can be the open at the customer premise. Still though, it shows us that there is an open circuit at 265 meters in this case. There are two ways of measuring an open circuit. The first one that we are going to discover is the capacitance meter measurement. That can be found on the basic copper menu, and it's number 2. This will give a good indication of the length where our open is located to. So if we choose number 2 and we perform the measurement, we should get the value in meters. In our case, we have a 265 meters open. Now, a second way of measuring an open circuit would be using the pulse echo tester, or otherwise called time domain reflectometer. That is the 4th function inside the basic copper menu inside the HST3000, and we are getting a signal trace where the open should be displaying in the right position. So if we change the display, we have a different set of choices that we can limit our pulse echo tester to the specified range of length that we are measuring, the range of test. In regards to the open circuit measurement, it's a good way of introducing ourselves with the PET and TDR functions regarding the different sort of settings that we can do. So in order to determine an open circuit, we certainly do need to use a PET, the pulse echo tester, or as what called time domain reflectometer. And we can see the following pictures that if we choose the 4th menu, which is the pulse echo tester, then we can just enter and look the trace of the signal over time that's being imposed on the pair of line that we are under testing. Now, in regards to our measurements, there are certain different options that we can use in order to allow ourselves to make the measurement more accurately and more efficiently. The first thing is, if we look at the pulse echo tester screen, there is an option there that allows us to change the range of the cable under test, the pair under test, that is. And we can have like the 6-4 parameters. The 6th one is the auto range, which is being auto adjusted by the unit itself to present optimal results. We can use this one for sure. But there are other cases where we are experiencing ghosts and phenomena that they are not very clear, so we need to specify the distance in order to acquire much of the unit, much of the results, that is. The extra short range, which is ranging up from 0 to 100 meters, the short range range ranging from 0 to 600 meters, the medium range from 30 to 2.5 kilometers, the long range to 300 to 5 kilometers, and the extended range from 3 kilometers up to 8 kilometers, which is the maximum that we can actually go in regards to VDSL functions. Section we said that we are going to measure an open circuit in regards to two different measurements. That is, we can find the length of an open circuit on a good line with two different ways. The first way would be of measuring the capacitive length of the line. How we are going to do that? Fairly simply. If we go in the copper measurement menu, that is the initial screen of the unit, first of all we have to connect our tip and ring again on the pair of our good line, that is from the pit to the customer premise again. As you see, this time I have opened up the line, so the line is clear and open at the other end, and we are going to try to measure this distance. In order to do that, we're going to the copper measurements and we are selecting number 2, which is the capacitance meter. So if we press OK, we let the unit do the calculations, and it clearly shows us that the line is 377 meters. We can also customize for aluminium and other custom variety of material regarding to the copper compromised of our line. The capacitance, though, we can measure also the capacitance if that's what our ticket of work is saying. So you can measure this value as well just by pressing display and changing from the actual copper. Copper will give you the length, and if you choose capacitance, will give you the capacitance value of the line for that distance. As I move along, I would like to show you that if we choose the actions button again and we're trying to choose the material of the cable gauge, so we can choose the actual material that the line is made of. So we can have a copper line with air filled pick or gel filled pick or palm of paper, which used to be the older type, or it can be a pretty fine loaded cable that we can select from a list. Now we can also predefine the cable gauge. That ranges usually from the range of values of 0.9, 0.64, 0.51 and 0.4. 0.4 is the most usual one when we are talking about jumper cables and interconnecting from the exchange, the pit, towards the customer premises. Now the only thing that we have to do is press Start Pulse Echo Tester, and that will trace up the whole line up to the point that the fault is found. So in this case the open is found. Another thing is that we can use the function of gain in order to achieve maximum resolution and be able to clearly see the various phenomena across the trace, that is, across the line that we are testing. So the gain has units of increase of 2, 4, 8 and goes up to 40. That is in order to make clear what kind of faults we are finding on the line and actually make them visually able to see them. So we can increase the gain by pressing the upward key, or we can select the time varying gain function, which provides a normalization factor to counteract line attenuation. This helps you outread faults that are very far from the test set by increasing the gain on the trace as the distance increases. Also, we can use Auto ID to identify the faults, and we can use the gain that makes the trace image looks larger or smaller on the display. Use the up and down arrow keys in the TDR mode to increase or decrease the gain, as we said before. As a rule, keep the gain in the lowest setting possible in order to see the events clearly. You can increase it gradually if you think that there is another problem associated with the line. Let's now jump. Let's now go to a hands-on video where I can explain most of these parameters talking on theory. Another way of looking at it would be using the pulse echo tester. Again, if we go in the copper measurement menu, we can go down and we can use the pulse echo tester. And we're pressing OK. Now, I want to make clear at this point that it says clearly, the unit says press start to begin the pulse echo test measurement. Nevertheless, there are some functionality here that needs to be shown. So if you go to options, you can select the range if you know how big is the range that you are testing for. So if the ticket of work says, for example, that the line of the test is 1.2 kilometers or 500 meters, then it's better if you use one of these options. Or you can just simply leave it to auto range. It will still do the job. Another thing is that you can, if you go to options again, you can change the velocity of propagation for the line, the cable field type. So is it filled with air? Is it the line filled with air? Or is it gel pick? Or is it pulp paper? Or you can load the cable predefined by your constructor. Now we can start by pressing Start Pulse Echo Tester. If we can see, we can clearly see, if I move the cursor, that there is an event happening at 258 meters. So if I increase the gain, that is, if I press the up button, then I can clearly see the event there happening. So the begin of the slope of the hill will be the final distance to the open point. Now let's say a little bit of a tip and tricks regarding the pulse echo tester. IFD. We can use this mode when a trace seems to be changing over time, so we can pick up the ghost effects. We can use the pick function that shows the current trace as a dark line and shows the highest and lowest traces as lighter gray lines, so you don't miss the changes and you can see the history of the trace. Maybe it's something changing towards the line over time, or maybe it's a cross effect of having an open and a short at the same time. Then you can easily pick up the distance of the fault and thus fixing it. The last trick should be that you can save the pet trace that you are currently working on, that is the line at the test being tested once with the pulse echo tester, and you can save this trace and load it as a reference so that you can see any differences or any big differences if there are phenomena that's happening on the line by interference, water ingression, or even from the exchange part of signal attenuation or amplification as well. A clean open will be the tallest peak other than the latch pass of the trace display, so that it's going to be the tallest peak as we move along and watching the trace on our screen. A dead short across the pair will be the lowest valley on the trace. We call that valley. Big events or reflections up close make things beyond harder to see. Measure from both ends if possible, and make sure the distances to the fault match closely. A pen can't see anything past an open, a short, or a load coil. The PET pulse looks like a high frequency signal, so load coils will roll off or decrease the amplitude of the pulse on any reflections. Shorts above 100 ohms will be difficult to see, or we can't see them actually at all. Measure to first false only and clear it before continuing. What I would like to show now is how we can use the IFD function. So if we again connect our line to the good line, right? I would like to do that first in order to begin. Then I'm connecting my leads on the good line. I'm making sure that they are not touching each other. So let's say that the line is open. That's going to be, we have to put a good earth point. Right? So if I run the pet now, I should be able to see the end of the line being at 257 meters. That's where our hill is. So that's where our line is open. Now if I press display and I choose the IFD function, right? If I can connect, if I can short circuit the 2 points, you see that I'm getting a short. What is basically IFD? It's a function that allows us to keep the previous graph compared to a new graph. So whatever phenomena are happening to the line and we are not being able to see them before this one happening, so it's like keeping the previous trace and we are doing a graphical comparison with a new trace. So in this way we can clearly identify ghosts or even intermittent mistakes that are on the lines and we cannot pick them up at once. So that's a very useful function for you to know and use out in the field, because it will enable you to find these faults and determine if they are actually faults or maybe they are phenomena that are being arised from humidity, instant humidity on a point, or a joint in a connector on an aerial splice. And by this way you can say that when an open becomes a short, or vice versa, a short becomes an open, then it should be a splice. Usually this phenomenon is happening towards the customer premises, where we connect our pair from the ground, from the tip outside the house premise, to the actual wall socket. Earth is one of the most important reasons that resistive as well as shortage are found on the lines under test. Keeping in mind that the length of the line under test is known to us by the ticket of order, once we realize that we are experiencing an earth short situation, an immediate action should be taken in order to locate the distance to the sorting point. This function is being performed by a resistive fault locate on the HST3000. In order to perform a resistive fault locate, we need to have two good starting points. That means the first one should be a pair of line that is good, or better if we have two pair of lines that we know that they are good. Now, as we enter in the menu, we can use two functions, the single pair manual strap or the separate pair manual strap. Mostly the one used is the single pair manual strap. You can select the right gauge by using the left and right arrow keys, and crucial thing is to choose the right temperature. That should be the temperature under which you are testing at the moment. That can be changed by the up and down keys. In order to perform the RFL test, the HST3000 black test lead has to be connected to the good wire. So the black one has to be connected to the good line we have in our disposal. The red test lead has to be connected to the faulted or bad wire that we presume that our error is. The green test lead is connected to the reference wire, which is typically the earth ground or shield. We need to put a strap along the black and the red, that is the good, and the faulted wire at the pit. Once we have connected the black lead to the good wire and the red lead to the faulted one, as well as the green to a good shielding point, which is the earth, and also we have made sure that we have put the strap along the good and the faulted line, then we can commence the test by pressing the Start RFL button. The parameters deduced from this test is 3. The DTS, which is the distance to strap, the DTF, distance to fault, DSTF, which is distance strap to fault, as we can see in the following picture. Once the test is finished, then we can see the respective values on the screen of the HST3000. You can see on top that we have the line to be a copper line of 0.51 millimeter thickness at the temperature of 20 degrees. Now, the fault depends on which point we are placing the HST3000 to. If we are looking at the pit towards the customer premise, then we have the black one, which is the good line, to be of 447 meters, which is what was given to us in the work of order. Then the fault should be at the 282 meters from the pit to the actual fault, and then 165 meters from the customer premise to the fault. Sometimes we may confuse wiring the leads correctly, but nevertheless the test will be still valid. Now, my friends, I'm gonna show you what happens in a line that is already faulted, and when we are experiencing, as we say, an earth phenomenon. When we are experiencing an earth, it means that we are having our leads connected to an earth by a water ingress or any other crossing fault towards our legs to the earth. In order to demonstrate this, I'm going to use this faulty line where I'm going to put my leads on, and I'm going to connect them. And as you can see, I have short-circuited the end of the line just for the purpose of the demonstration. Now, for the sake of it, I'm going to connect my earthing point, the earthing point of the unit, to the end of the line, just to make the measurement more precise, and just for you to see that the instrument is performing up to the specifications. So initially we have to run a resistive fault test. So if we go into the default menu we are going to go to the display and select the resistance snapshot. As you can see, both the tip to ring, the ring to ground and tip to ground are all earth. So that means that they are all short circuited to earth. They are connected to earth. So we are experiencing a short circuit phenomenon in both legs. And that can be clearly shown by the value of the resistance in each of the elements. Now, my friends, I'm going to explain to you how earth short circuiting becomes a problem to our lines under test, and how we can overcome this phenomenon with the precision of the instrument by using the functionality of the instrument. An earth condition would imply that both legs or one leg is grounded to the earth. So it's being short-circuited at some point along its length to the earth. So if we take out this faulty line, I'm going to connect the tip to the tip, the ring to the actual ring, and the earth, just for the precision of the unit, I'm going to connect it at the end of the line. And if you can see, I have short-circuited the line at the end. In order to discover that we have an earth fault, we said that we are experiencing a resistance, a higher resistance. To discover that, we need to just go to the default menu, select the resistance snapshot. If we go to resistance snapshot, and we are waiting for the instrument to give us the value. So the values between the tip to ring is 0.5, the red to earth is 0.05, and the black to green is 0.03. That means that our both legs are short-circuited to earth. So we are experiencing high resistance. That means that the line is not good. So in order to discover the distance that this fault comes into realization, and in order to correct it actually, we need to go and we need to go out in the main menu, and we have to select the resistive fault locate. That measurement will pinpoint where the fault is along the line. So if I press OK, the test begins. So we have pressed start RFL, and now, as we can see on the unit, we are trying to locate the distance to strap, distance to fault, distance strap to fault. So actually these two distances, to fault and distance strap to fault, when we are looking from the unit, from the pit actually, towards the customer premise, or from the customer premise to the actual fault, that's the distance strap to fault value, length value, will pinpoint where the fault is. So with this way, we can locate exactly the position along the length of our faulty line. Remember that the tip has to be connected, well, the black lead has to be connected to the actual good pair, and the red one to the faulty pair. Now both pairs were faulty, and for the sake of it, I have, if you look closely, I have reversed the leads, just to show you that the unit, even with reversed leads, can pinpoint where the length of the fault is. So if we look closely, we have 197 meters of a good line, and at 168 meters, where I have turned my switch to be, it's the fault. It's so simple as that. and then you can go on that point, and maybe it's an aerial splice, or maybe it's in the pit just before the customer premise, that you have to undo the cable and re-splice it again. Move the foreign battery test. As we all know, foreign battery indicates contact between the test pair and another working circuit, that is another working pair. To measure this fault, we have to take the line out of service, drop the battery at the exchange, so we can see the end of the line. Then the second simple step to do is run a voltage snapshot. We should have values of less than 3 volts in AC and DC conditions between the tip ring, ring to ground, and tip to ground. The below measurement indicates the presence of foreign battery onto the line under test. That is because the tip ring, even though we have disconnected the battery from the exchange, we are experiencing a 0.4 volts in AC conditions and minus 26.6 DC volts in DC conditions. That indicates that a neighborhood pair is crossing ours. Still, we can use the RFL function to locate the fault once more. Now we are going to move to the bridge tap situation. So what is actually a bridge tap? A bridge tap is essentially an extraneous length of dangling, unterminated cable on a communications line, usually left over from an earlier configuration. A bridge tap can cause an impedance mismatch and have undesired effect in our transmission line. In order to determine a bridge tap, we have to measure the capacitive length of the line and also to compare it with the resistive length function of the line. We can use the pulse echo tester to locate the bridge tap. So, in order to make sure that we are in a bridge tap situation, and to summarize the situation, we have to compare the capacitive length together with the resistive length measurements that we are performing with our HST3000. And then, as a final step, to use the PET function to locate the bridge tap. Here we can see that we are performing a distance to short, and as we open the far end, we run the capacitance meter. Clearly can be seen that we have a difference of 130 meters between the two. Once we have determined the difference in distances between the capacitive and resistive length, we surely know that we are in a situation where a bridge tap is among our line. Now the only thing that remains is to locate the bridge tap and remove it from the line. If we are going to employ ADSL 2 services or even plain HSDSL, then we have to remove the bridge tap. We can run the pulse echo tester that will clearly shows us where the bridge tap is located to, and that is clearly at 153 meters, which was the difference between the capacitive and the resistive length that we saw before. Now visually, a bridge tap should be a valley followed by a hill in our trace graph. We can run the time varying gain to get a clearer trace, and moreover to indicate that the presence of the bridge tap. In this section, we are going to demonstrate how we can recognize a bridge tap by looking at the screen of the PET function on the HST3000. So in my fault box I have the faulty line, and for the sake of it I'm going to turn the switch number 2 where I have a bridge stop fault. What is basically a bridge stop? A bridge stop is a point of the line that we have tapped in order to transfer the line to another point. Usually in the older days when they were deinstalling lines, they were leaving the bridge stops there. So it was like having two lines being equally splitted, or not equally splitted, being splitted at a point. So in order for the line to be clear and open again and be able to have the full functionality of it, we need to discover where that bridge stop occurs. The way of going about it is that we have to use the pulse echo tester. If we choose the pulse echo tester, then we press start. If you can see, if I minimize the gain, I'm seeing a really small dip at 51, 52 meters, 56 meters, 57. So if I increase the gain, because it's really important that you have to play with the gain. It's really important, because the gain will be the one that indicates what kind of mistake, what kind of fault is on the line. So if you look closely, we have a really sharp dip there, followed by an increase, a hill. That has to be a bridge stop. That is considered to be a bridge stop because, as we said before, a valley is a short, which is what a bridge stop essentially is, and then it's followed by an open, where it heads towards where our eyes went. Here are some typical pulse echo tester traces. It's a nice form of graphical representation of the various faults found on the lines under test. The first one is an open. We can clearly see that because the attenuation is getting lower and we're having a clear hill. The second graph, it shows us a short, that is a valley. Still the attenuation, as we can see it, is gradually decreased. Now a wet section is something more tedious to work with, but clearly you can see that we have a valley followed by a small hill. That's a wet section. Actually, the small part of the hill is due to the inductance going into the line by the water ingression. The fourth graph is a bridge stop, and as we said earlier in our presentation, it's a valley followed by a clear hill. Now, a loaded coil, we have a different graph, similar to an open, but as we can see, the attenuation is not being decreased in a linear form. We're having a sharp increase and then a gradual increase. A high resistance joint or splice, it's the opposite of what a bridge stop is, and that is a hill followed by a sharp, if you like, in a sense, valley. Balance on the line is the most important of all for the line to be able to carry next generation ADSL services. The third menu inside the copper measurements, it has the length and trans noise balance. A value of greater than 60 dB would be sufficient for a good line. That is, would be sufficient for a line to run a DSL service on it. Here are some values for the tone, because tone is measured in dBms, and some values for the noise that are measured in dBRN. Here are some values for the tone, because tone is measured in dBms, and some values for the noise that are measured in dBRN. The following is a diagram from which we can understand where our testing point is. In order to understand basically what ADSL service is and where is located from and to, we can see that we have the ISP, Internet Service Provider Gateway. We have the DSLAM, the PSTN network. We have a port splitter, and in between we have the copper loop pair, the copper twist pair that we are running the tests. At the far end we find again the port splitter that gives us the plain old telephone service, and a modem or router that gives us the digital subscriber service. That is data, and as well as video. So the uplink is clearly shown to be from the customer to the network, and the downlink from the network to the customer. Our primary concern when we are testing ADSL2 service would be both of these parameters, with a special attention to the downlink, which is why the customer is paying for. ADSL workings. So how does actually ADSL works? We said before that we are using discrete multi-tone modulation. It's a type of modulation. If we see at the following diagram, the plain old telephony, which is the voice, it's considered to be the yellow bit ending at 4 kHz. Then we have the downstream packet, which is from 20 kHz up to 160 kHz, and then we have the from 24 kHz, 2400, I may be excused, kilohertz. We have the bit packet, which is the downstream signal. Everything is controlled by the ADSL protocol. We have reached the point where we can clearly see what our ADSL test points are. So in the copper loop, we have to make sure that the copper is able to sustain and support ADSL services in all times. We have the means by the use of the HST3000, the DVOM and all the rest measurements to verify that the copper is capable of sustaining these services, as well as supporting them. As we're moving on further, we need to increase our knowledge and perform some ADSL testing. So clearly our test points at this point are changing. It's the DSLAM, and it's just before the router at the customer premises. So we can actually test from the customer premises plug and see how our ADSL service is running on the house. In the following table, we are going to see the test criteria that qualify our copper line as to be able to sustain and support services. So if you can see, we have the parameters as AC voltage for 100k ohm meter to be less or equal to 25 volts to be acceptable. The DC voltage less than 6 volts. The insulation resistance should be greater than 2 mega ohms, as well as the leakage test as well. Loop resistance has to be less than 1300 ohms. The tip to ring vs ring to ground difference should be 10 ohms at maximum. The capacitive loop length cannot exceed the 15.5 kilofeet. The capacitive balance should be of a capacitance difference of 5%, as well as the longitudinal balance greater or equal to 60 dB, in order for our line to be noise free and balanced to carry on with the ADSL services. In order to commence with the ADSL service test, first of all we have to choose the second tab on our HST3000 that says XDSL. X stands for any technology related to DSL. That can be the symmetrical DSL, digital subscriber line, the asymmetrical one, or even VDSL. Now the unit can be used in two ways. It can be a terminal modem that can sense and test all the parameters to the line, or it can be done in the through mode, checking actually the data within the line. In this example, we are going to see how the unit is performing a modem router test, where it trains up its internal modem and it's synchronizing, sensing the line under test to give us all the parameters of the line that the customer is currently using. That is the actual rate, the maximum rate, the capacity of the line, the noise margin, line attenuation, which is of high importance, as well as signal attenuation. As the modem is synchronized, we can clearly see in the first screen that the unit can give us the estimated length from our test plug, that is the customer's plug on the wall, to the dish lamp that is on 1.9 kilometer distance. This value is different for each case. And then we are going to see the actual rate, the maximum rate, the capacity, noise margin, line attenuation and signal attenuation. It's best to keep in mind that the noise margin should be at around 7 dBm for the uplink and 6 dBm from the downlink. We can also see the GINP statistics from the local and remote, that is the downstream, and the upstream. Also, we can use the unit to see what kind of errors we are getting, like the loss or frame loss, the forward error correction, the forward error correction per minute, the cycle redundancy check, the cycle redundancy check per minute, the loss of frame per second, and the loss of also, when we are running the test, the unit helps us out here and it gives us an XDSL signal table that everything is being explained according to the ticket of work. That has to do with the upstream and downstream service, as we are checking for ADSL 2 services. That's the line attenuation, the signal attenuation, the transmission power, interleave delay, actual in-noise balance, and the attenuation regards to 1 MHz. We can see the modem software version that we are using with our current HST3000, as well as the modem chipset. We can get also the XDSL graph that gives us the bits per tone and the attenuation, the power of the signal along the frequency range. So if we look at the graph, we can see that the first part is the pods, is the voice in other words, and then we are getting the upstream as well as the downstream. One thing that we have to say at this point is that we can alter the ADSL general settings. So depending on the provider and the lines that we are testing, we can change different modem parameters. If we hit the configuration button under modem, then general, we can see what standard protocol we are using. We can add that from ADSL 2 to whatever protocol we are using. We can also choose in between Annex A or B when we are talking for PSTN or ISDN services. What kind of transport protocol used? In the present case, it's asynchronous transfer mode. We can have the physical rating settings, we can have the bit swapping, the 24K interleaving depth, the DSL interface, which is an RJ45, the core minimum margin and the layer 2 lower power. Also, we can have the bonding group or parameters, and we can set up the up rate, the higher up rate, the low up rate, the download rate, the high download rate, the low download rate, the maximum download rate, and all these settings. Overall, in this presentation, we have covered much of the aspects, the test functions, and the multifunctionality of the unit, and how all these functions link together to help us perform our test and measurement more safely, more securely, more completely, and more accurately than ever before. Thank you very much for your attention.